Hi everyone, we are going to do all of chapter 3 next, and that's going to be how to measure angles instead of in degrees. We're going to talk about how to measure it in radians. On your calculator, we talked in the last section about how to do typing things in degree mode. In this chapter, we're going to go with radian mode, and so along the way you might want to switch your calculator back to radian measure. So there's a button that has the D or G on it, usually on a lot of calculators. The D changes it to degree mode. The R would be radian mode. And then G is gradians. We don't actually do gradians. There's a weird story behind gradians, but a lot of the stuff that we'll be doing in this section, and then several sections to come, will actually be in radian mode. When you go to calculus, everything is measured in radians. That's kind of the more mathematical way to do it. So let's talk about what an actual radian is. So in order to do algebra on trig functions, we have to have real numbers, not have degrees. So degrees from 0 to 360 degrees doesn't translate very well when you try to do things, graphing and a few other things like that. And so we want to change it to something that's not degrees, and we call them radians. Radians is not technically a unit of measure. We'll put radians after it just to let you know that it is not in degrees, but it is not the same sort of idea as it would be if you were saying that a length is 5 feet. The feet would be the unit. Radians is not really a unit though, it's just a number. So an angle in standard position that intercepts an arc on a circle equal to the length of the radius of the circle has a measure of 1 radian. And so, well, what does that mean? Well, it kind of looks like this. If you were to have an XY plane, this is going to be an awful looking picture, I know, but it's okay. And you had a circle on the XY plane. This length right here would be the radius of the circle. And so if you had a radius going out this direction, 1 radian is where it says the angle intercepts the arc equal to the length of the radius. This length of this arc right here, this is also 1 radius long. And so if that's true, then the angle that's in here, this theta, is 1 radian. And so to go back and forth between the two, we know that 2 pi radians is the same thing as 360 degrees, and we'll use that kind of idea to go back and forth how to switch them from radians to degrees. So if we want to switch from degrees to radians, we would multiply by pi over 180. I just said that 2 pi equals 360, so if you could cut that in half on both sides, you get pi and 180 would be the same thing. So using pi and 180 is a little bit easier. So if we want to convert from degrees to radians, like for instance a 45-degree angle that will pop up a lot of the times in several different sections, we could take that 45 and multiply it by pi over 180. And we tend to like to leave the pi in there, and so what you'll notice is that 45 will go into 180 4 times, and so this is pi over 4. So an angle of pi over 4 is the same thing as an angle of 45 degrees. Or if I was to do 90 degrees, if I took the 90 and multiplied it by pi over 180, well, 90 goes into 180 2 times. And so this becomes pi over 2. So an angle of pi over 2 would be the same thing as an angle of 90 degrees. We can get into some bigger numbers, like 450. That's okay to do as well. If I did 450, I do the same process. I do 450 times pi over 180. And that one's not quite as easy to simplify, but you might notice there's a 0 on the end of both of them. So they're both divisible by 10. So it's 45 pi over 18, but 9 will go into both of those. 9 goes into 45 5 times, and 9 goes into 18 two times. So this is actually 5 pi over 2 if you put it as simple as possible. It'd be 5 pi over 2. Now, if it's a decimal or if it has minutes and seconds in it, that usually means that the pi got absorbed into it, and so we'll have to put that in the calculator. So I still do the same process. It's still 42.5 times pi over 180, but instead of leaving the pi in there, we would multiply it all together. So you would go to the calculator, type 42.5 times pi divided by 180, and you'll get a decimal number. It's about 0.74-ish, depending on how many decimals you want to go out to, or 7.4. If you want to do another one, 7.42. Or, like on this last one down here, this one's in minutes and seconds. So you might want to take the 10 minutes and divide it by 60. You'll get 1/6, which is a repeating decimal. It's 0.166666667, depending on how many decimal places you want to go out to. And so I would take the 139 degrees in 10 minutes. I'd make that 139.16667, ever how many decimals you want, and multiply that by pi over 180, and type that in the calculator. Oh, that right there was supposed to be a curved line. And so we'll take this, multiply it by pi, divided by 180, and you'll get about 2.43. That's a 4, by the way. Radians. Preferably, we would like to keep the pi in it and keep it in its exact value as possible, but sometimes that's not possible. And so we can type it in the calculator if need be. Okay, let's go the other way around, doing the same basic thing. If it has pi's in it, then we will have a pi to cancel off, because we will be multiplying by pi on the bottom instead of pi on the top. And so we'll multiply by 180 over pi. So I would take the negative pi over 6, multiply by 180 over pi, and if it is exact, you'll notice that the pi's will actually cancel each other off, and 6 goes into 180 30 times. So this is negative 30 degrees. Or if I did pi over 3 times 180 over pi, again, the pi's would just cancel. And then you say that 3 goes into 180 actually 60 times. So this is exactly 60 degrees. If I do that with 4 pi over 3, I would take 4 pi over 3 and multiply by 180 over pi. Again, the pi's cancel. Here, 3 goes into 180 60 times, just like it did on the previous one, but I do 60 times 4, which is 240 degrees. And you could type this in the calculator if you really wanted to. Now, on part D, it just says 2 radians. And I still have to do the same process. I still multiply by 180 over pi, but there is no angle. There's no pi in my angle. And so we'll have to just go to the calculator and say, what is 360 divided by pi? And you get about 114.59 degrees. That's about what 2 radians is. And I do the same thing on the last one down at the bottom. We have one that's just 1.74. So 1.74 times 180 over pi. 1.74 times 180 divided by pi gives me about 99.69 degrees, somewhere in that area. And so it's going to be important for you to know how to switch back and forth. Mainly, it's more important to go from degrees to radians, especially for those of you going into calculus. But going both ways is not very hard. .2 is applications, and there's actually two main applications that we want to look at. One of them is the arc length, and one of them is the area of a sector. So the length, the arc length on the outside of the circle, it would be labeled S. And so if you had a picture, this is kind of like that picture of the circle I drew earlier. You have a radius R and a central angle theta and an S to give you the arc length. So this would be a radius. So your radius is R there. You'll have an angle, doesn't matter where it is, maybe we put it over here. So you have an angle on the inside that is theta. Your arc length is S, and so that's the part on the outside of the circle. This is S. And it's a formula, S equals R theta, where theta has to be in radians. And so the central angle is the little light blue theta there, the angle with the vertex at the center of the circle. And the arc length is the distance around the outside. And using that same sort of thing, the area of the sector, the area would be kind of like the filled in part where the theta is in my little picture up here. That area is given by 1/2 times r squared, the radius squared, times theta in radians again. So those are the two main formulas we'll be looking at in this section. So for instance, this says find the exact length of the arc. So to find the exact length of the arc, I just have to do those two formulas. And so for this first one, the 6, this is your r. The pi over 2 is your theta. And we're looking for the length of the arc. That would be the part on the outside. That would be S. So S equals r theta. We just plug the numbers in. The r is 6. The theta is pi over 2. So the length on the outside is 3 pi. The arc length is actually measured in the same units as the radius. So if the radius is 6 feet, then the arc length is 3 pi feet. So on this other one, the 8 is the r. The 5 pi over 4 is your theta. The arc length would be the part around the outside, like this. That is your arc length. So your S equals r theta, which would be 8 times 5 pi over 4. 4 goes into 8 2 times. 2 times 5 is 10, so this is 10 pi. And that would be the length of the arc. Now you could find other pieces, like instead of finding the arc length, you could find the angle or the radius using the same formula. Here, the 12 is my S. That's the length around the outside of this circle. The 6 is the R. I'm looking for theta. So if S equals R theta, I'll have 12 equals 6 theta divided by the 6. Theta is 2 radians. Or, like we saw on that other page a while ago, 2 radians is about 114 degrees or so. Okay, this is the same type problem except without a picture. But we don't really need a picture for these type problems to just find the arc length. Your radius, notice all these radii are in decimals. Usually if you have a decimal for a radius, they probably want you to type it in the calculator. So that's what we'll do. I'll say that S equals R, 12.3, times theta, the 2 pi over 3. I'll go to my calculator over here that you all can't see, but it's there, trust me, and do 12.3 times 2 times pi divided by 3. And I'll get that my arc length, they have 1 decimal on the radius, so I'll do 1 decimal as well. It'll be 25.8 centimeters. And notice the arc length and the radius have the same unit. On part B, I do the same thing. S equals R 1.38 times theta, which is 5 pi over 6. Again, go back to the calculator. Do 1.38 times 5 times pi divided by 6 gives me a arc length of about, this has 2 decimals, so I'll go 3.61 feet. Now part C has an issue, and that issue is my angle. It's in degrees. I can't have an angle in degrees. I have to have it in radians. So I have to pause on this one and say that I have to take this 60 and multiply it by pi over 180. And 60 goes into 180 exactly 3 times. So I'm going to use pi over 3 for my angle and say that S equals R 4.82 meters times pi over 3. So 4.82 times pi divided by 3 gives me about 5. This has 2 decimals, so I'll go 2 decimals, 0.5 meters. Or close enough. Now we can do some word problems along with arc length as well. One type thing would be find the distance between 2 cities. And we can do that because technically the Earth is a sphere. So a cross section of our Earth would actually be a circle, give or take. It's actually a little bit oblong in the middle, but don't worry about that part. And so as long as we have 2 cities that are on the same north-south line, or actually you could do it east-west as well, but we're going to do north and south, we can find the distance between them using the arc length formula. So for instance, the Panama City, Panama, not Panama City, Florida, is at 9 degrees north, and Pittsburgh, Pennsylvania is at 40 degrees north. Can we find the distance between them? And the answer is absolutely. Why could we not? So I'm going to do the arc length formula. S equals R theta. So I kind of have an angle. If they're in the same hemisphere, both north or both south, you will subtract the angles to come up with your theta. So here my theta will be 40 minus 9, which is 31 degrees. I don't want it in degrees, so I have to change that to be radians. So it won't change very well because I'll just take 31 and multiply it by pi over 180. But 31 is a prime number, so it won't simplify. So I'm just going to leave it 31 pi over 180. And that'll be my angle. Now, you'll have to know what the radius of the Earth is. And some people say that's common knowledge and some people don't. Since we're in kilometers, the radius of the Earth is about 6,400 kilometers. If you don't know that, now you do. And so then my arc length would give me my distance between the cities by using the radius of 6,400 times 31 pi over 180. And we type that in the calculator and see what happens. So I'll type 6,400 times 31 times pi divided by 180. And I'll get those 2 cities are 3,400, and I'm going to round to the nearest whole number, 63 kilometers apart. keeping in mind your radius being 6,400, you cannot possibly get two cities further apart than the diameter of the Earth, which would be 12,800. And so if you got two cities that were further apart than 12,800 kilometers, one of those cities would have to be in space somewhere. So don't do that. Now on the next one, it says between New York at 41 degrees north and Santiago, Chile at 33 degrees south. In differing hemispheres, one north and one south, I have to add my angles together. So I have to do 41 degrees plus 33 degrees to get 74 degrees. Again, change that over to radians. And this one does simplify. 74 is even, so you can simplify it. But I'm not actually going to worry about it because I'm going to type the whole thing in the calculator anyway. My radius is still 6,400, just like it was on the last one. And so my arc length would be my distance between my cities of 6,400 times 74. Uh-oh, I left the 4 off, didn't I? Not just 7 pi, but 74 pi over 180. And then we go back to the calculator. 6,400 times 74 times pi divided by 180 gives me an arc length or a distance of 8,266 kilometers. So that's how far apart my two cities are. This one's a little bit different. This one says Madison, South Dakota, and Dallas, Texas are 1,200 kilometers apart. Since they are 1,200 kilometers apart, then I can do the arc length formula and say that the one city is at 33 degrees north. I can find the other city using the arc length formula. So here, this 1,200 kilometers, that is my arc length. That would be like my answer on the previous page. And so I would take that 1,200 and use my formula that S equals R theta. I know the R is still 6,400. And I plug those two numbers in. So I'd say that 1,200 equals 6,400 times theta. And I solve for theta. So if you divide it, 1,200 divided by 6,400 would be theta. So I go to my calculator and go 1,200 divided by 6,400 is 0.1875. That's in radians. I don't want it in radians. I have to have it in degrees. So I'll have to take this 0.1875 and multiply it by 180 over pi to put it back in degrees. So if I multiply that times 180 divided by pi, I get, and I'm going to round this to the nearest whole number, it's 10.74, or it's about 11 degrees. Now here's something you also have to know about the map. You have to know that South Dakota is north of Dallas, Texas, because when we do our angle, we will say that our distance, our angle that we came up with was subtracting the two or adding the two. You have to know that they're both in the northern hemisphere, that you would have to subtract them. So my angle for Madison, South Dakota, that I'll call X, would have to be subtracted from the 33 degrees from Dallas, Texas to get the 11 degrees that I just found down here. So if you add the 33 to both sides, then you get about 44 degrees north is where Madison, South Dakota is. If they were in opposite hemispheres, then you would have it added and then you subtract it back off. Okay, let's talk about area of a sector now for a moment. If we do area of a sector, I need the radius and I need the angle. Like here, I don't have that. The 2 pi in this problem is actually the arc length. But I could use the arc length formula to come up with the angle. And so I could put 2 pi equals the radius of 4 times theta, or 2 pi divided by 4 equals theta. So theta is actually pi over 2, or about 90 degrees. It kind of looks like a 90-degree angle anyway. My area formula, my area of a sector, is 1/2 r squared theta. And so here I would do 1/2 times r, which is the 4, squared, times the theta I just came up with. 4 squared is 16. Half of 16 is 8. And 8 times pi over 2, oh sorry, 8 times, yeah, that's what I said. 8 times pi over 2 is 4 pi. The area is measured in square units of whatever the radius is. So if the radius was 4 feet, this would be 4 pi square feet. So the area is actually all of this stuff inside here. So going the other way around, this says you have 12 pi square units. So they're saying that this is the area. All of this side, all this stuff in here is 12 pi square units. They want you to find out what the angle is. Looks a lot like a 90-degree angle to me here too, so we'll see what happens. But my area is 1/2 r squared theta. Here the area I know is the 12 pi. The radius is the 4. So I'll get that 12 pi equals 4 squared is 16, so half of 16 is 8. Divide by the 8 on both sides. And that does simplify. 4 will go into each one. This is 3 pi over 2. 3 pi over 2 is a multiple of 90. That's why it looks like a 90-degree angle. It's actually 270 degrees if you switch it back. So this angle would be measured around this direction. That would be your theta. Okay, doing it without the pictures, we're going to type most of this in the calculator. Find the area of the sector where you have 29.2 meters for the radius and the angle is 5 pi over 6. So, like I said, we're going to type most of this in the calculator. It's just 1/2 times the radius squared times the angle. Just be real careful on typing this in the calculator when you do type it in the calculator. But I'm going to do 1/2 times 29.2 squared times 5 times pi divided by 6. And I'm going to get a area of 1116.1. This is measured in square meters because the radius is measured in meters. Now the second one, part B, you have an angle that's in degrees. I can't have that degrees. So I'm going to have to take this angle of 81 and multiply it by pi over 180. You have to be in radians. And so you could leave it just 81 pi over 180, or you can simplify it. 9 will go into both of them if you want to. I'm not going to worry about it. We're going to put it in the calculator anyway. So my area will be 1/2 times the radius, 12.7 squared, times the angle, which is 81 pi divided by 180. And we go back to the calculator and see what happens. 0.5 times 12.7 squared times 81 times pi divided by 180 gives me about 114. It's one decimal, but one decimal after that would be 0 anyway. This is square centimeters because our units are centimeters on the radius. Okay, how about a word problem? The area of a lot. So there's a piece of land that needs to be surveyed, and they're not usually perfect straight lines when you do surveying. And so in this case, we might have, say, a railroad or a street making this curved line out here. And so that makes a sector for this part. And so I need to find the area of that sector and then the area of the triangle. The area of the sector, the part that's new in this section. 60 degrees is not good for the angle. So the angle being 60 degrees, I actually need to turn that into radians. This is actually one of the angles that we've already done. This is pi over 3. 60 goes into 180 3 times. So I have an angle, but I don't have a radius. But I can come up with the radius fairly easily. My radius would actually be the hypotenuse of my triangle. And I can come up with the hypotenuse just by doing the Pythagorean theorem. If I do 30 squared plus 40 squared equals, I'll call this side C. Then I'll get 900 plus 1600 is C squared. So I'll get 2500 is C squared. If you take the square root on both sides, you'll get that C is 50. 50 yards. Then I have a radius. That 50 is my radius as well. So my area of my sector is 1/2 times 50 squared times pi over 3. And we go back to the calculator and type that in. 0.5 or 1/2 times 50 squared times pi divided by 3. And you'll get 2 significant digits is going to be about 1300. This is measured in yards, so this is square yards. That's just the area of the sector. I then need to find the area for the triangle, which you might remember is 1/2 base times height. My base is the 30. My height is the 40. So half of 40 is 20. 20 and times 30 is 600. And so the total area is just add those together. Would be 1300 plus 600, which would be about 1900 square yards. And that would be my answer for that one. Hopefully that's not too terribly bad. Okay, the last section in this chapter where we're going to talk about is the unit circle. And this is probably one of the more important things that you'll want to know going into calculus is how to figure out what these angle measurements are. You can do all the stuff that we did back in chapter 2 on reference angles and 30, 60, 90 triangles and stuff like that, or you can do the unit circle. I like the unit circle, but that's not the only way to do it, and some people don't like the unit circle. So this is our last definition of trig functions is in this section. It's basically the same definitions we did back when we did trig functions the first time, when we did sine is y over r and cosine is x over r and tangent is y over x. We're going to use those same things, but we're going to apply that to the unit circle. And the fact that it's a unit circle, that unit is 1, and that 1 is the radius. So we're still doing y over r, but the r is 1, and we're still doing x over r, but the r is 1. And so it's a little bit different with that kind of idea. So the unit circle looks like this right here. And so if you've never seen it, it can be kind of confusing or a little bit intimidating, but it's really not that bad. This is the same ASTC chart that we talked about before, where they're all positive, sine and its reciprocal are positive, tangent and its reciprocal are positive, cosine and its reciprocal are positive. So it's the same chart that we talked about then, except now we have both radian measures, degree measures, and points along the way. These points make up the trig values. These would be the sides of your triangle. Like for instance, take this 30-degree angle right here. If you went out to that point and went straight down, you would have a triangle. And the length of that side would be the x value and the y value. The x value and the y value are the point. So since I know that sine is the y over the r and the x over the r for the cosine, then the x value would just be cosine. So all the way around this chart, your points are cosine of the angle and then sine of the angle, because the r is just 1. And so if I was to ask what is cosine of 30 degrees, you would say square root of 3 over 2, because that's the x value at 30 degrees. And you go all the way around the chart. The first quadrant is the 30, 60, 90 triangles and the 45, 45, 90 triangle. That's what that first quadrant comes from. If you want to memorize the chart, you will have to have it memorized if you want to use the chart in Cal 1. But if you'll notice, all of the angles correspond. So they all match. If you went straight across, the points are the same. If you went straight across, the points are the same. So you only have to really memorize the angles themselves and whether or not you're positive or negative. Same thing vertically as well. The points would be the same. And so it's not terribly hard to memorize. If we were in class, I would actually give you a quiz on it, trying to memorize it. Since we're online, though, I won't be doing that. It's kind of up to you if you want to try to memorize it. But all the important thing is that your x and your y coordinates are the same thing as cosine and sine. If you want the other 4 trig functions, tangent is still y over x, or the other ones, secant, cosecant, and cotangent, are still the reciprocals. So find sine of s, cosine s, tangent s if s is negative pi. Now negative pi is not technically on the unit circle, but if you rotate, I have the top half of the circle down here on the bottom. If you rotate the angle positive pi, you would end up on a straight line. You would rotate it this direction to get to positive pi. There's your positive pi right there. If you were to rotate with a negative pi, you'd still end up in the same spot. So the fact that it's positive pi or negative pi on the pi doesn't really matter. So sine of negative pi is the y value at pi, which is 0. Cosine of negative pi is the cosine value, the x value, which would be negative 1. And tangent of negative pi would be the y over the x, which is also 0. The unit circle makes it fairly easy to look at and just pull values off pretty quickly. So these next few slides will be actually going through kind of fast. So hopefully this makes sense. This says find the exact circular value as well. And it says find sine of 7 pi over 6. So all you want to do is go to 7 pi over 6, which is right here. And sine of 7 pi over 6, sine is the y value, so you just pull the y value off. The y value is negative 1/2. Which, had we done it back in chapter 2, you would have taken 7 pi over 6, turned it to degrees to make it 210 degrees, used the reference angle of 210, which would be 30, take the value at 30 for sine, which would be positive 1/2, and then make it negative because you're in quadrant 3. So instead of doing all of that, I'm looking at a chart and pulling a number off. So like, for instance, 3 pi over 4. 3 pi over 4 is right here. And it says do tangent. So tangent at 3 pi over 4 is the y value, which is root 2 over 2, divided by the x value, which is negative root 2 over 2. And if you're dividing the same values on top and bottom, you just get 1. One of them is negative, so it's negative 1. Please notice, all the way around the circle, all the denominators are all 2. So if you want to figure out tangent, all you really have to divide is the numerators. You would still get negative 1. Okay, cosecant of 11 pi over 6. 11 pi over 6 is right here. Cosecant is what you get when you flip over sine. So I'm going to take the sine value, which is negative 1/2. I'm going to take this negative 1/2 right here, flip it over to get negative 2. And that's the cosecant of 11 pi over 6. Now, 23 pi over 6 is not on the unit circle. The unit circle stops at 2 pi. It goes all the way around and ends at 2 pi. And so since it stops, anything beyond 2 pi, you have to adjust for. And so the easiest way to do that is subtract 2 pi off of it. And say this is 23 pi over 6 minus 12 pi over 6. So you have to do a little bit of common denominators here. But 23 minus 12 gives you 11. This is also the same angle, 11 pi over 6, that we just looked at. Since it's secant, I'm going to take the cosine value and flip it over. So the cosine value, I'm going to take this value and flip it over to give me 2 over root 3. Or if I rationalize it, pull the radical up to the top and drop the radical sign off on the bottom, gives you 2 root 3 over 3. And that would be my answer. Okay, now we're going to look at trying to do calculator approximations for radians. So here you notice there are no degree symbols on the numbers, the 0.6109 or the 94946. There's no degree symbol, so we assume that these are going to be in radians. So we'll want to make sure that your calculator is in radian mode. So it'll either have an R or an RAD at the top of your calculator instead of a D or a DEG. And basically we just type them in and see what we get. So sine of 0.6109, you can just type that in. And remember, sine will give you a number between -1 and 1. So this will give me a value, since it's got 4 decimal places, I'll go 4 decimal places as well. 5736. And that's all you really do. But like we've discussed before, I don't have a cosecant or a secant button on my calculator. So I'm going to do that with a reciprocal. And cosecant, if you flip that over, you get sine. So I will do, this is 1 divided by sine of -9.4946. And again, we're just going to go to the calculator and type it in. 1 divided by sine of 9.4946. And here, since it's technically cosecant, we should get a bigger number than 1 or smaller than -1. But I ended up with 14.3338 if you take it out 4 decimal places. And that would be my answer. Okay, this says evaluate the 6 circular functions of a value for t. And so you'll notice that we have the angle is t here, and then we have a 5/13 and 12/13. That is the point that is the angles intersecting this circle. And we're assuming this is the unit circle since the angle t matches the arc length here. And so if I want to do what is sine t, sine is just the y value, so you just write it down, 12/13. Cosine t is just the x value, so you just write it down, 5/13. And tangent t is when you divide them. Again, notice just like on the unit circle, the denominators are the same, so you technically only have to divide the numerators. So tangent would be the y over the x, so the 12 over the 5. And the rest of them you just flip over. Cosecant would be 13/12. Secant would be 13/5. And cotangent would be 5/12. And there's not a whole lot of work to show there. You're basically just looking at that point and trying to determine all the different values from that one point, which is pretty easy to do. Okay, now we're going to go the other way around doing the inverses in radians. So make sure your calculator is still in radian mode. And we're going to find these using the calculator. So tangent s equals 0.2126. Again, we're looking for the angle here. I don't know the angle. So anytime you don't know the angle, you have to do the inverse. And so my angle s would be tangent inverse of 0.2126. And you might say, well, I thought s was the arc length. And it is. On the unit circle, it doesn't matter. They are the same thing. Your angle and your, because it's a s equals r theta. So if your r is 1, s and the s of the arc length and the theta of the angle are the same thing, which is kind of an oddity, but oh well. So we're going to go second tangent and go 0.2126. And so that'll give us an answer of about, since it went to 4 decimal places, I'll do 42095. Again, we don't have secant inverse on our calculator, so we're going to have to change this to be cosine of some sort. So if you do the reciprocal of each one, this is cosine is 1 over 1.0806. And so then I can do cosine inverse of 1 over 1.0806 and type that into the calculator. Very much like we did one very similar to this a little earlier. So I'll do second cosine of 1 divided by 1.0806. Close that off. And I'll get a S, or an angle of, S by the way, 0.3887 if we go to 4 decimal places. Okay, now this says find the angle. Here we're looking at the unit circle, anywhere between pi and 3 pi over 2 where sine is -1/2. This is one of the major reasons I like the unit circle, because a lot of times you're just looking at the circle to figure out what the answer is, as opposed to doing a lot of reference angles and going backwards. We did one similar to this at the end of chapter 2 with, well, at the end of 2.2, I believe, when we did reference angles. And it was a lot of moving stuff back and forth with reference angles. This, though, says go between pi and 3 pi over 2. Well, here's your pi, and here's your 3 pi over 2. So this basically just says quadrant 3, because we're in between this area here. And we're looking for where sine is -1/2. Well, remember, sine is your y value. So you're looking for where is your y value negative 1/2? Well, it is right there. There is a y value that's negative 1/2 at 7 pi over 6. And that's your answer, sitting right here. And that's why I like the unit circle. Okay, let's do one word problem. You might know this. Temperature is periodic. And so anything that gets repeated after a certain period is usually mapped with some sort of trig function. Periodic meaning that in the summer in Mississippi, you can pretty much assume it's going to be hot. In the winter, it'll be cooler, not cold, but cooler. And so that up and down in the temperature swing is a periodic function. So because values of circular functions repeat every 2 pi, you can do periodic graphing with those. And so we have a model here of a temperature. The temperature T equals 60 minus 30 cosine x pi over 6. T represents the maximum temperature in the afternoon, starting with 0 being January, 1 being February, and so on. So I'm going to do for the month of September, mainly because my birthday is in September, so that's why I picked that month. But it could be any month. So September x would be 8, if you're starting with 0, 1, 2, 3, 4, 5, 6, 7, 8. So 0 going with January, 8 gets with September. And so all you have to do is say the temperature is 60 minus 30 times cosine of 8 pi over 6. Well, 8 pi over 6 does simplify. That's the same thing as 4 pi over 3. And 4 pi over 3 is on our circle. It is right here. And so cosine is the x value. So this negative 1/2 that's sitting there is my x value. So cosine of 4 pi over 3 is negative 1/2. So I'll get 60 plus 15, and I'll get a temperature of about 75 degrees. This is measured in Fahrenheit. I'm guessing 75 degrees Celsius would be bad, so we're going to go with Fahrenheit. It might be on there somewhere, I don't see it. But anyway, 75 degrees Fahrenheit would be pretty pleasant for September. 75 degrees Celsius, you would probably be dead from heat exhaustion. So, but that's all you have to do. You're picking off the value off the unit circle, plugging it in, and seeing what you get. You could also type it in the calculator, and it would come out exactly the 75 degrees, as long as you have radians on your calculator. So hopefully that makes sense. That's all of chapter 3. We're going to go on to chapter 4, which is all about graphing.